So the purpose of this video is to have a look at the electrolysis topic in the GCSE Chemistry Double Award specification. There is a separate video for straight chemistry. So let's have a look at what does electrolysis actually mean. Well, obviously I think you should be able to work out that the electro part refers to electricity and the lysis means to split. So essentially what we're doing here is we're using electricity to split not molecules, to split ionic compounds, actually to split electrolytes up into their constituent elements. And this is a really useful part of chemistry. It's where your aluminium comes from, it's where lots of your metals come from. Okay, so let's have a look at a little bit more about electrolysis. So the definition, electrolysis is the conduction of electricity by an ionic compound. Note this only works for ionic compound. That ionic compound in this particular instance is known as the electrolyte, and that electrolyte has to be molten or dissolved in water. Okay, and that leads to the decomposition of the electrolyte. In other words, the decomposition of the ionic compound. And it very nicely decomposes into its elements as far as we're concerned anyway. Okay, now you might be asked, why does the electrolyte have to be molten or dissolved in water? Well, that's because the ions have to be free to move. If you remember back to last year, you would have learned that ionic compounds can only conduct electricity when the ions are free to move. And the ions are only free to move when the bonds are broken. And the bonds are broken either by melting it, making it molten in other words, or dissolving it in water. So electrolysis, the passage of an electric current through that liquid, causes it to decompose. Right, the liquid being decomposed is called the electrolyte. Again, that's something that you have to know. It's an ionic compound. Okay, and again, we've already said it's molten or dissolved in water so that those ions are free to move and they can carry charge. That would be your definition of an electrolyte, and it's your definition, or your explanation, as to why that electrolyte has to be either molten or dissolved in water. When you have a solid ionic compound, the ions are in fixed positions and they will not be able to migrate to a positive or negative electrode. So that's what an electrolyte is. If we have a look at this video here, hopefully it will show us so the reaction. So let's have a look at what the electrodes are. So we've covered the electrolyte, we've covered why the electrolyte has to be molten or dissolved in water, we've covered their definition of electrolysis and what it is. Let's have a look at what the electrodes are then. So the electrodes are, very simply, as far as we're concerned, they're just metal strips or graphite rods. Both things conduct electricity. They're placed into the liquid, which is the electrolyte, and they conduct the electricity into that liquid. They carry electricity into it. Okay, they are called inert electrodes in this particular instance. Okay, and inert electrodes are simply good conductors, high melting point, but also importantly, they do not interact or react with the electrolyte. Remember, the electrolyte here is very often molten. It'll be at high temperatures, so chemical reactions tend to happen more readily at high temperatures. So it's important that your electrodes in this instance are what we call inert electrodes. They don't partake in any of the chemistry involved in the electrolysis. So that's the sort of diagram below there that you guys will have to be able to label. I don't think they'll ask you to draw it. They may well do ask you to sketch it, but you certainly do need to be able to label it. When you're labeling your electrolyte, which in this instance is lead bromide, you must make sure that you label it molten lead bromide. Don't just call it lead bromide. Okay, they want an understanding from you that you know that it's liquid. You have over here a positive electrode. That positive electrode is called the anode. Causes difficulty sometimes because positive ions are called cations, and therefore a lot of people think the positive electrode should be called the cathode. It's actually called the anode. So I used to remember at school, anodes attract anions, remember. So anodes are, and I always remembered that anions were negatively charged, so therefore the anode had to be the positive one. Okay, so don't get those two things confused. Over here we've got the negative electrode, and the negative electrode is therefore called the cathode. Alright, and make sure whenever you are drawing them, if you are, that your positive terminal of the battery is actually linked to your anode. Okay, So let's have a look at this in a little bit more detail. So our negative pole, which we have here on the right hand side, is the cathode. All right, it attracts cations. So remember, cathodes attract cations, and provided that you can remember, which is important, that cations are positively charged, you should remember that cathodes are negatively charged. The opposite happens on the other side, of course, where we have our graphite rod in this instance, which is our positive anode. Okay, and remember, the positive anodes attract anions. Anions, hopefully you remember, are negative. Therefore, anodes must be, of course, positive. So let's have a look at the general setup of electrolysis. We're going to do a sort of a case study here on, we're going to use lead bromide, and I'm going to show you how you'll be asked by an examiner to work out what products are made during the electrolysis of a particular compound. You'll be asked what will you observe at the cathode and what will you observe at the anode. You'll be asked for half equations of the reaction that happens at the cathode and the anode. That only applies to higher tier, so if you don't do higher tier, if you're doing foundation tier, don't worry about the half equations that happen at the cathode and the anode, but you do need to know everything else. So the first thing that I do, or that I would suggest that you do whenever you're asked to do this for a particular compound, so we've given you lead bromide here, is you should work out really the formula of lead bromide. Okay, that will allow you to work out the ions that are in lead bromide, and that is really important, that you get the ions correct and you get the charges correct. Now, some of you may not have to work out the formula to know the ions that make up lead bromide. That's fine, whatever, provided you get to the correct formula with charges of the ions. That's all that really matters here. Okay, now we make this molten, okay, and we set it up in the apparatus slide. So don't worry about me flipping through slides. I'm flipping through slides that I've spoken about already, so you're not missing anything. Okay, and we set it up as so. Again, this is a type of a diagram that you may well be asked to label, so make sure that you are able to do that. The lamp is in this one that was in the last one. The reason why we put the lamp in is just so that we know that the actual cell is working and that electricity is in fact passing through it. Right, so let's have a look at what happens at the cathode, and then we'll deal with the anode in a little second. So remember, we're doing lead bromide. We've already worked out that the positive ions are lead 2+ ions. So there, what is going to be attracted to the cathode? So our lead 2+ ions are attracted to the cathode. Now here's the rule of writing half equations in electrolysis. The substance that is made as a product from the ions is just the element in its standard state. So for example, if it's lead 2+ ions, we make, as you would find in the periodic table, lead metal. Just lead metal. That's all we make. And now the second rule is the only thing that you can balance a half equation in electrochemistry and electrolysis using are electrons. You will always have electrons either on the left hand side or on the right hand side, but they must balance the charges. We're always used to balancing atoms in an equation. We now have to make sure the charges are also balanced. I'm going to show you how to do that in a little second. Right, so lead 2+ we can sort of say is short of electrons. It doesn't have enough electrons, therefore it's positive charge. It somehow at some point has lost electrons. It needs to gain electrons then to become pure lead. Remember I said earlier that everything in electrolysis becomes the element, and remember elements have no charge. It's only ions that have charge. So my lead is 2+, and my lead ions are 2+, and my lead on the right hand side has no charge. So if I ignore my electrons for a second, I have 2+ on the left and I have 0 on the right. I have to have those two charges balanced, but I can only balance them with electrons, and each electron has a -1 charge, remember? So therefore I need to add 2 -1 charges to the left hand side, or in other words 2 electrons. So I have +2 and then plus the 2 electrons, so +-2 or -2, and that equals 0. So both sides are 0. 0 equals 0. That's okay. So that's how you go about every single electrolysis half equation. You start with the ion on the left, you finish with the element on the right in its standard state, and then you work out the charges left and right and balanced by using negatives, electrons only. Right, that lead therefore has gained electrons. We've gone Pb2 plus the 2 electrons, so we're showing it's gaining the electrons, and you should know from previous redox topic that reduction is the gain of electrons. So this is a reduction reaction. You'll be asked to classify that as such. The next part of this is what would you see? What observation will you get? Well, you're making lead down here, okay? You're making lead around the cathode, and it's being made in a very hot temperature, okay? So it's going to be molten. And what does a molten metal look like? Well, it looks like kind of like silver beads. I've written silver globules there, silver beads. Okay, so some sort of understanding that it's like a silvery molten liquid of lead. Okay, now here's the good thing. Every single electrolysis that you carry out at GCSE Double Award has a metal formed at the cathode. So the observation, when there's a metal formed, which is every one on the spec, that's not to say they may not give you another one, okay, but it is 99 times out of 100 a metal, and therefore the observation is silver globules or molten silver liquid. Right, let's have a look at what happens at the anode. So at the anode, we said earlier, lead bromide was made up of lead 2+ ions and bromide ions. So at the anode, we're going to have bromide ions. And what are bromide ions going to become? Well, they're going to become, as I said earlier, the element. And the element for bromide ions is bromine. Now, here's where you need to be a little bit careful this time, because bromide ions are Br minus, and bromine in its standard state, okay, at room temperature is Br2. So we have to be cautious with that. We have to balance up the atoms in this one before we get to charges. Okay, so we need to put a 2 there. You never put, by the way, I'll just write it down here, you never put Br minus with a small 2 down there. That is utter nonsense. Okay, bromide ions exist individually on their own, not with another bromide ion. If you think about it, if you want to explain, two bromide ions are both negative. They'll repel each other. They won't join to make Br2, which implies that they are bonded together. Okay, so that is what you have to do then. If we look at the equation, we have 2 Br negative on the left and we have Br2 on the right. So on the left, my charge is 2 negative, so it's -2, of course. And on the right, it's bromine. Remember, all elements are 0. I need to bring the right hand side down to -2, so I'm going to add 2 electrons to that. Okay, this time the bromide ions on the right hand side have the electrons in them, and now we're showing that the electrons are separate from them by putting this plus sign in. That tells me that electrons have been lost from the bromide ions when turning them into bromine gas or bromine liquid, and that is oxidation. So this half equation here is oxidation. Now what would you see? Well, if you go back to your periodic table study last year, whenever you did halogens, you did what the halogens look like. So for example, bromine is an orangey brown, pungent, bleachy smelling liquid. So you will get exactly that. Here you will get a brown vapor, because remember, bromine is under high temperatures here, and bromine itself will boil at about 60 degrees Celsius. So it doesn't come out as brown liquid, it comes out as a brown vapor, and it is a horrible, pungent, smelly gas. Okay, smells of bleach actually. It's a good thing to write. It smells a bit like chlorine. Okay. This is done in the fume cupboard, as are all the electrolysis reactions which involve the production of a halogen, because halogens are all toxic. Okay, so just be careful of that. That's a question they often ask. Why is this done in the fume cupboard? Don't just say because it's toxic or because a product's toxic. You have to be specific about what is toxic. In this case, it's bromine. Okay, so you're going to do some here, okay, in which you're going to predict the products at both electrodes. You're going to write balanced half equations and label them as reduction and oxidation. You don't have to do the yellow one if you're doing foundation. You're going to state the predicted observations at the cathode and the anode, and you're going to say how you could test for any gas that happens to be made at them. Okay, so there's the 4. You can pause the video. I'm going to run through the answers here, but you can pause the video, okay, and do them, and then check the answers. So for the first one, we have lithium chloride. We've said it's made up of lithium ions and chloride ions at the start. That's what I would do. At the cathode, which attracts the positive ions, the lithium ions are going to turn into lithium metal. That means that it needs only 1 electron. Okay, that means that it's reduction. You're going to see silver globules because lithium is a metal, sorry. At the anode, you're going to have chloride ions, okay, from lithium chloride. Okay, that's going to turn into chlorine gas, which is diatomic. You should know that. So I'm going to have to go back here and put my 2 on here, and I'm going to need 2 electrons on the right hand side to make both sides minus 2. Your electrons are being lost this time, so that is categorized as oxidation, and chlorine is a sort of a green, bleachy smelling gas. How do you test for chlorine? You test it by using damp blue litmus paper, and that damp blue litmus paper goes red and then goes white. You must say the litmus paper is damp, by the way. Okay, if you want to pause the video, okay, we're going to go down and do the calcium iodide one next. Okay, no we're not, we're going to do aluminium oxide next, sorry. So we're going to do aluminium oxide. Okay, so aluminium ions are 3 plus, oxide ions are 2 minus. So aluminium will go to the cathode, it will turn into pure aluminium, the element. That will need 3 electrons to cancel the charge out. Again, it's a metal, silver globules, dead easy. We have gained 3 electrons, so it is a reduction. At the anode, we have our oxide ions coming down, and that turns into oxygen gas. Remember, oxygen gas is diatomic, so I'm going to need my 2 here. Okay, this is where some people get caught out. I have 2 O2 minuses, so I have a total charge on the left hand side of 4 minus. So I'm going to need my 4 electrons on the right hand side. Very often we get an answer where we have 2 electrons on the right hand side here, which is wrong. Okay, on the right hand side we're making oxygen, which are bubbles of just a colourless, odourless gas, and your test for that would be to relight a glowing splint. Okay, on the right hand, on this equation, sorry, I should have said that electrons are being lost. They are now separate from the oxygen, and therefore we have oxidation happening. And finally, we'll do the magnesium one. So magnesium nitride, okay, so we're made up of magnesium ions and of nitride ions, okay. Those are the correct charges on them, very important that you do that. The magnesium goes from magnesium 2 plus to, like I said earlier, just 0 charge elemental magnesium. So we need 2 electrons on the left hand side to balance the charges out, plus 2 here. 2 minus here, that gives us a 0 charge on the right and the left both. It has gained 2 electrons, plus 2 electrons means it's gaining them, so that's reduction. It's a metal again, so dead easy, silver globules every time. Down here we have nitrogen 3 negative ions, or nitride ions I should say. They go to nitrogen gas. You have to know that nitrogen gas is diatomic. Okay, that means that I need 2 of these. Never put your 2 down here, okay. And that means I have minus 6 on the left hand side, 2, 3 minuses. So I have 0 here, I need minus 6, so I'm going to need 6 electrons here. Nitrogen is a colourless, odourless gas, so that's dead easy. You have shown that the 6 electrons are now separate from the nitrogen or the nitride ion, so you've lost 6 electrons, so your reaction is oxidation. Your test for your nitrogen gas is that you do all the other gas tests and they're all negative. So therefore you can assume that your gas is nitrogen because it doesn't actually give a positive gas test. Guys, I hope that's of some use and allows you to understand the electrolysis topic. Okay, any questions, let me know.